先生、女士，欢迎来到椰林讲座。本次演讲的主讲人是中央研究院刘立芳院士，主题是一位台大校友的学术生涯。Ladies and gentlemen, welcome to the NTU Royal Palm Lecture Series. Today we are very honored to have Dr. Philip Liu to share with us an NTU alumnus academic journey.演讲开始之前，让我们掌声欢迎国立台湾大学陈文章校长，也是本场演讲的主持人，为我们发表开幕致辞。
今天的主讲人也是我们的校友，杰出校友，我们刘立芳刘院士，以及我们廖副校长、张副校长，我们教务长，还有我们总务长，以及我们今天有几位院长来参加，包括这个文学院的郑院长，还有理学院的吴院长。还有这边应该主要是理工学院的各位老师各位同学大家午安。今天我很高兴来介绍我们的杰出校友刘立芳刘院士来给我们台大椰林讲座。这个是我们的第二场，我们第一场事实上是在9月1号的时候邀请了我们日本名古屋大学的天野浩诺贝尔奖物理奖的得主来举行这个椰林讲座。那椰林讲座在我们学校是属于学校里面等级最高的一个讲座。那主要就是我们来邀请这个知名的诺贝尔奖得主、院士、杰出的校友、名誉博士、杰出的企业家来给演讲。所以今天我们特别请到刘院士。那我来介绍一下刘院士，他是1968年。我们台大土木系毕业，那毕业以后在 MIT 在74年，给梅强中梅院士拿到了这个博士学位。事后他在 Cornell 就展开了非常长期的一个学术生涯，升到了教授以及担任土木系的系主任。那2016年之后，他在 Cornell 那边退休，到新加坡国立大学担任副校长的职位。那期间的话，他跟台湾有非常多很密切的这个学术上的来往那之后他在应该是2年前左右我非常幸运的能够有机会来推荐我们刘院士为我们本校的杰出校友。那2年前也接受我们学校颁证杰出校友。那后来的话，我想这个刘院士在结束新加坡国立大学的生涯之后，目前是在这个成功大学担任玉山学者。我们非常也很希望有机会能够刘院士来到台湾大学来担任玉山学者。另外，他也是中央大学的李国鼎的讲座不过我想今天真的非常难得，他讲的题目今天非常的科普，纯粹就一个校友立场来告诉我们说，一个台大的这个校友是怎么样来度过他这么长期的学术生涯，又这么杰出。那这边很多人可能都是他的学生，他在学术生涯里面supervise 非常非常多的这个学生。目前在世界上各地担任教职就有30几位。实际上更了不起的是他在海啸、波浪力学这边有非常杰出的成就，不只是获得了美国的院士，事实上他也是中央研究院院士，他也写了很多本书，那个书是非常精彩，而且出版了一系列的这个有关于这种波浪力学方面的这个专书如果世界上提到海啸或者波浪力学方面，我想我们刘院士是世界上首屈一指的。虽然我知道他今天可能不讲波浪力学，因为有很多 equation， 所以他今天讲了一个不同的 story。不过我想这样的科普题目应该大家都是非常欢迎的。另外，我也跟各位报告，非常高兴碰到刘院士，因为他以前就是在我们院里面担任我们的评鉴委员。我那时候为什么会推荐他的原因是会跟土木系说我要推荐刘院士担任杰出校友，是因为他有一次到我们院里面来应该是应力所推荐他当这个评鉴委员，我就对刘院士他在学术上这些的意见我想说一些建议对院的发展我非常的欣赏，所以刚好有那个机会推荐他。那今天中午我跟他吃饭也获得他很多的启发另外也跟各位报告，我本来还有点不太舒服，跟他吃完饭以后突然就是充满了正能量，现在人也好了。所以我们是不是以热烈的掌声来欢迎我们刘院士，我们的校友。
Okay, so microphone, right? All right, great. Well, thank you, President Chen, for the introduction, very kind introduction. And it's really an honor to be invited back to give this a second speaker of this seminar series. And I'm also very, very happy to come back to Taida, the campus. And just before I came to here, I was given a tour of the university's history museum, and I almost cried. And honestly, listening to the so-called 校歌, okay, and 望春风, right? All right. Anyway, when I was invited to give a talk, honestly, I have never been so worried and so nervous about it. I have given hundreds technical talk in my professional life, but this is the first time I was asked not to show a single equation. So also I was told that most of audience are young audience, and anybody is younger than me anyway. So I really don't know what to say, and which might be of interest to at least some of you. So I asked some of my friends and colleagues for suggestions, including my former PhD students. So luckily, I get a response from one of the former PhD student who happened also to be a professor at NTU right now. And this is really just a copy of his email, right? He basically told me that, look, think about it, who you are, who I am. And he thinks I like math, which was true. And I like ocean waves, like President Chen, that I spent a lot of time, my career study ocean waves, looking at different kind of waves in oceans. And one of them happened to be tsunamis, which is a very, very long wave. And I just love doing research, right? I mean, research is my life, basically. And then, you know, I can spend all day long talking to anybody who wants to talk about research, science, technology, so on and so forth. A little bit obsessed about it. So some people probably cannot bear talking to me for too long because. Anyway, as a result of my long career, I suppose, that I built up a very small but very close cluster of friends, professional and otherwise, and they're all over the world, spreading out many continents, and also have many students, as the President Chen mentioned, that I have something in order magnitude of 30 PhD students, and most of them are actually professors, and most of them are staying as a professor throughout their entire career. What does that mean? I don't know, but I think it's a good thing. And so we keep in contact and over all these years. And I have a professor as young as assistant professors, all right, and just starting their career. I have former student who has already retired after they have been provost or president of universities. So I just outlast a lot of them, that's all. So most important thing he said, I think it's also true, I seem to be really love or like what I'm doing. I really enjoy what I'm doing. And that the kicker is the last one. He said, based on his experiences talking to the young people in Taiwan or NTU students, they don't realize that there's such a person like me exists. In other words, I can have this lifestyle, right? Enjoying doing what you're doing, getting involved, interacting with young people, and doing research, searching for the truth, and enjoy it, the daily life like this. I was told that nowadays, most of the students in engineering or even science, their goal is going to Taijidian. I'm sorry to mention that. But overwhelmingly, over the last couple of years, I talked to different professors in different universities, especially in engineering. They said that no matter what discipline or department the students are in, whether it's civil engineering, chemical engineering, or whatnot, their goal is going to Taijidian, get a job in Taijidian. Why? Money. Right? Income is higher. You have more incomes. You can fulfill your material life. And it seems to be something is missing in that kind of process of deciding what do you do, what do you want to do with your life, all right? So he encouraged me to say, why don't you say something about how did I do it? How did I actually get involved into this business, doing research, teaching, all right? And perhaps, hopefully, this is what I'm saying now, hopefully over the next 30 minutes to 40 minutes, couple of stories I'm going to tell you about myself and will trigger something in your mind. Think about there's an alternative than looking for money or career, deciding your career based on fulfillment of your material life, right? So he simply suggests that's the outline of my talk, all right? I said, that's cool. That's fine. Let me try to frame my talk around these items, and I probably will not be able to cover all the aspect of these items. And fortunately, I understand there was a Q&A section. So if I missed something I didn't say or you want to know, feel free to ask me later on. All right. Besides, I really want to say that I'm not planning to give a seminar because I'm not allowed to write down equations, right? And I'm not really going to give a tech talk or inspiration type of talk, not really. I would consider today's gathering here is a simple conversation between a very senior researchers, senior in the sense of age, to share his experiences in his career, in his academic career, with a group of younger colleagues and students, colleagues. All right? I think everybody in here is younger than me, so I can say younger colleagues. All right? So it's just a simple chat, simple conversations. Let me share something about myself and my experiences, and hopefully will inspire here and there one or two of you to do something I really think is fantastic to have a career like that. So to do that, I have to go back and give you some history, especially very young group of students in the back. Right? So I was born, so we're going back to history now. I was born in 1946. Right? And so my parents moved us, family of, let's say, 5, from Fujian to Taiwan in 1940, my gosh, I was 48, I think. So I was a little bit over a year and a half old, all right? And my father basically packed us up and bought the tickets and get on a boat, and we came from Fujian or Fuzhou, I don't know which harbor is it, to Taipei, to Keelung, actually. So basically the family is a refugee of the war, okay, between the war between, anyway, the war. And so I don't think I really understand it. I can understand how did they get through that period of time, right, during the wartime, and how did my father actually have the courage he didn't have a job. He didn't really have a job in Taiwan when he come over, only because a friend of his said that, well, there are some opportunities here. That if you come over, maybe you can find a job in such and such a place. And he packed up all five of us, whole family, to come over, just like that. Right? That probably has something I took his gene a little bit. That's how I sort of carry out myself in my adult life. Anyhow, so we did okay when I was a little kid, and we can have enough to eat, and they can send us to school, and I managed to do reasonably well academically, right? But I was never a student sort of working very hard trying to get to the top of a class. I was probably doing okay on top of 10%, 50% of a class, right? And so you can call I was one of those kids, a little bit smart, have some smart in the head, right? And also is good kids in the sense that going with the flow, not rebel, didn't rebel against whatever the parents want you to do. So I did okay. I went to the elementary school in Beishi Fu Xiao, right? Then I went to the high school, junior high and senior high in Sida Fuzhong. Both are pretty good school, right? I like sport. I play a lot of basketball, but probably I wasn't very good at it. And also I wasn't taught enough. Nevertheless, I spent a lot of time in the basketball court, right? I didn't study very hard. I have to emphasize that. And that's important because there is a consequence of that, right? Now, when I reached the so-called senior year or end of senior year of a high school in Sida Fuzhong, and surprise, surprise, they say, hey, you can go to Chenkong University. Here's a connection, right? I'm paying back, actually. Chenkong University, that you don't have to take exam, general exam, what we call 保送, right? And a whole bunch of us, there's about seven of us. You probably recognize which one is me, right? Probably so obvious, right? This one. Yeah. Okay, so bunch of us actually also get this waiver of exam, and I don't think everyone, I think 4 or 5 of us. So you can go to the Chenkong University without taking an exam. But Chenkong University at the time is only called 省立成功大学, right? It's not even 国立成功大学. Also, you know, Tainan at the time, this is 1964, right? Tainan is like in foreign country, right? and I have never been in Tainan up to that point, never been in Tainan in my life, right? And far away place, my parents said, no. You don't go to Tainan, you take an exam and see whether you can get into Taiwan University, National Taiwan University, right? And being a very nice kid, right? And say, okay, I won't go, I will take exam. But some of my kids, my friends, very close friends here, they all went to Chenkong University. Okay, so I took an exam, and fortunately, I did good enough to get into Taiwan University, and in fact, get into civil engineering. And today I went to the museum. They showed me a yearbook, the graduation, the yearbook. And I saw my picture in there, and it's number 3 in the row, on the first top row. That means I was a number 3, top number 3 in the entrance exam to civil engineering in 1964. Right? I probably did very well in the entrance exam, but that's not the point. But it is a point. I was kind of surprised that I would look at the left and look at the right. We compare the notes. what kind of a score you get in the entrance exam. Oh, you get a 90, no. You get a 90 in the math, but 40 in the Chinese. Then I got a 40 in math, 90 in Chinese. Did I say that right? But anyway, we all get into the same school, and because at the time we have to take a Chinese and 三民主义 and physics all equally weighted, right? So the system wasn't perfect. That has some impact on me. I just said, this is a ridiculous system, right? But anyway, so I got into the civil engineering at National University, Taiwan University. Everything seems to be okay. Everything seems to be fine. But there was trouble ahead, right? When I get to the Taiwan University, you probably realize, I don't know how you feel now today. At the time, in a high school, elementary school, high school, school is very structured. You have everybody take the same classes. You sit in the classroom, and teachers come in to give lectures and assign homework. But when you enter the Taiwan University, probably just like today, then you decide, well, there are some required courses, some very few select courses, but you still have some freedom of choice. And also, in fact, you have a freedom of choice not to go to the class. Right? In high school, there's a 教官, right? And just marching around the campus that they're catching you if you don't go to class. But in Taiwan University, there's no such things. Now, of course, again, it's because the teenager things, you start to think about your life, you think about other things. And guess what? I didn't go to classes, right? So I did, but I didn't go to all the classes. Especially the classes in the Saturday afternoon, which happened to be calculus, right? And so I missed almost all the calculus courses I have to classes I said. And the consequences is that I failed the final exam of freshman calculus. Right? Failed. I don't know how many of you failed any classes in the university or not. But anyway, I feel horrible, right? And but fortunately, at the time they had a policy saying that you failed the class exam, but you didn't fail that badly, so I give you another chance. Come back after the summer, take a makeup exam. If you pass it, you can move on. I give you a passing grade, probably D or D minus or whatever, and then you can move on, right? But if you fail that test, sorry, you have to retake it again, so on and so forth. That means that you have to delay your progress, or graduation, perhaps even affecting that. So that was a wake-up call, and that was one very important event in my life, all right? And that's the first time I realized that, well, I have a choice to make. And do I want to do this? Or do I really want to study it? Or do I just saying that, okay, I mean, that's the way it is, and I probably would just give it up and do something or retake the course later on. But anyway, so I spent that summer basically alone on the beach of Hualien, right? At the time, my sister lived there. So I did a lot of soul searching. Believe it or not, for a 19-year-old, that was actually quite a shock things for me. So anyway, the decision is that I'm going to do it, all right? And I'm going to do it this time, not just for the grades. And I conscientiously say that I'm going to learn this subject, all right? And I spent the summer actually studying calculus by myself. And I sort of like it, At the end, I really like it, and I think this is fun, somewhat, right? But so ace the makeup exam, and move on. Not only for the calculus course, and I also decided that I really, since I'm here, having these opportunities, I might as well learn something. And so in the sophomore year, I actually Oh, this is my beautiful picture, young picture. So the second year, the sophomore year, we have to take more courses in engineering mathematics and also engineering mechanics of materials, and fluid mechanics. And those are all very applied math oriented course, and also mechanics oriented course. And believe me, I really studied it. I studied it not for the grades. I actually studied it for the knowledge, trying to really understand what's going on. Actually, I learned something that I have a bunch of friends in college too, that in the class, the best way to learn the material is to teach your friends. You know, NTU has a bunch of very smart kids, but not everybody wants to study very hard. But when you have a buddy who is willing to give you a cram course or cram whatever, get together, and I volunteered, I trying to teach them, tutor them how to do it, and that's how I actually learned it by myself. All right, I do learn a lot of details in those classes, and also another big plus things during that time is that some of these courses I mentioned, like engineering mathematics and also engineering mechanics courses, were taught by some young instructors, lecturers, 讲师, right? These are young master students. They just got a master student. They stayed on to help teaching. Those teachers are these people really enthusiastic. They really want to teach, and that really inspired me, right? And I really think, wow, you know, they really love what they are doing, and there must be something in there, right? Now, in particular, I want to mention one professor. Some of you probably recognize him very well, right? 叶超雄, 叶老师. And he was actually my engineering mathematics professor. He was just a fan. One of these professors that he just loved teaching and loved interacting with young people, and he was willing to spend as much time as you want. He was trying to explain what's going on in the courses he taught, right? And he and Mrs. Yan usually routinely invite a student to his house, and we're sitting around chit-chatting, not just about the coursework, but everything else, right? So that really developed this environments that you really enjoy this interaction between professors, your teacher, and the students' environments, right? That made a really great impression on me, and that almost, I believe also perhaps affects some other classmates in my class. I did a quick survey just before when I prepared this talk or conversation. These are the names of my classmates in that class. We have about 30-something, 40 students when we graduate, I think, in the class. And these are the people that I can find out. They turn out, they become the professors in the different places, including 3 of them are Taiwan University, 2 of them in Tumushi, okay? And that probably means something, right? I mean, you did something good. I mean, you really convinced some of the students as you come back to return to teach the next generations, right? And Yang Deliang, Hu Weite, Zheng Futian, these are the 3. I think Zheng Futian is in Huangong Environmental Engineering, the Research Institute of Environmental Engineering. Then there are other places, other peoples in the different universities. And interesting enough, I have to say something, okay? Most of us, except Zheng Futian, were all study fluid mechanics. Okay, we're civil engineering at the time. We don't even have an environmental engineering. The major subject is structure engineering, right? But all these students actually turn into study fluid mechanics. I don't know what's the correlation, what's the really driving forces behind it. But that's just an interesting thing to point out. Okay, so when I was in the junior and the senior years, and I started to take quite a few courses that outside of civil engineering, right? But you have to realize at a time that the curriculum was set up in such a way that most of the courses are required courses. In each discipline, you have many required courses, very few slots you can take from outside. And a couple of my classmates, we were probably just thinking outside the box, or were thinking ahead of a time. We say, doesn't matter, we will take extra load, right? We're going to take some of the courses that we think we really like. For example, I went out to take an advanced calculus course. It's equivalent to mathematical analysis in the math department. That's crazy, right? For a civil engineering student, junior student, and take a mathematics course, analysis course. Besides, that course conflict with the water resources course in civil engineering. And that course was taught by the famous 徐世大老师, okay? But for some reason, the departments sort of close their eyes open and just say, okay, if you can manage it, not get caught by the professors, and you can pass the course, that's your business. And I actually managed to take both courses almost in the same time. Right? Now, another kids, like Su Zhongzhou actually took some modern physics course in the physics department when it was junior year. And in the senior year, I went even more crazier. I took a lot of graduate courses in the department, like theory of elasticity, structure instabilities, complex variable. I literally finished half of a graduate course program for the master degree at least, right? And especially in solid mechanics aspect. Maybe that's why drive me to go to the fluid mechanics, because I took all the solid mechanics courses already. But the reason I said that is I want to give credit to the university, to Taida, being allowed us to do such crazy things, right? And I think we'll probably push the boundary a little bit, push the system a little bit, but they somehow allow us to make those choices. We probably take on extra loads to fulfill what we want. Right? So I know the situation is very different now, but the spirit is the same. Right? Think about what interests you, and make a decision, make a choices, and you need to follow the rule, for sure, but you can always commit yourself to do something extra, right? To work on what you really would like to do. Because this is a precious 4 years, right? If some of you are still undergraduate student here, this is the time you trying to discover yourself. I don't think you can do that in high school, especially in the system we had in at the time. But college life, because it's being more flexible, because it's being more open, right? Explore your own interests. Find out who you are, basically, what you like, what you don't like, what the courses you like, or other kind of things you like. And this is very important 4 years. And you're at the right age, you have enough of energy, you can do a lot of extra things, right, to help you discover that. Now, tell you what, I mean, I was in civil engineering for 4 years, but my conclusion at the end of the 4th year is I don't want to be a practicing civil engineer. Right? Because a lot of courses I took in civil engineering, to me, is too mundane. You know, a lot of design courses, and you follow the rule book, you design it, and you get a number, you get an answer. And also there is some business aspect of being engineer or civil engineering. You have to prepare the contract. You have to be able to deal with the situations around the bidding of a contract, and so on and so forth. Fortunately, at the time, actually, we had such courses that professor would come in to tell us these kind of practical thing, right? And I just simply realized that my personality really doesn't fit into that kind of career path, right? Just not me. I couldn't do it. On the other hand, because I have taken some other courses, exploring many different kind of courses, I realized that I really like kind of asking questions, trying to find the truth, and doing some scientific research, right? So I simply decided at the end of 4 years that I'm not going into practicing engineering immediately. I want to pursue advanced studies. And in fact, the fact is that I have taken all the courses in the graduate school, more or less. Maybe the option is to go overseas to get advanced degree in the United States in this case. So that was me. I simply used that 4 years wandering through up and down, and that's the most important result, right? It's not about the grades you get or anything like that. It's that you find out a little more about yourself, and you start to narrow down what your interests are, what do you like to do, perhaps for the rest of your life, maybe. So anyhow, so that is the decision, right? Of course, I have to serve in the Army for 1 year, and I served the Army 1 year, well, in the so-called armor division, the 装甲兵, right, for 1 year. That year happened to be the 10th anniversary of Bar 3炮战, right? You're way too young. You don't remember that. You don't even know that. That is the, well, anyway. So everybody was quite nervous about it, especially in the military, right? So I was really serving in the Army, in the military that year. We drove the tank from Gangshan all the way to Taoyuan, all right? And come to Taipei and park the tank in the Songshan Jichang, right? To defend the Great Taipei, right? For this national holiday, I guess. But anyway, speaking of that, right? I think to me personally, again, the military service was very good for me. Very, very good for me, because up until that time, all my life is in the university, in the school. All the people I'm dealing with are with a similar kind of background, students or teachers, right? But in the armies, that forced me to deal with people coming from all sorts of different backgrounds, educational background, economical backgrounds. I grew up a lot in a very short period of time, right? And how to deal with these kind of real life situations, so to speak. And so in some sense, I also encourage young people that if you have a chance, go out to the society to do something, right? And find a way to gain some practical experiences, right? Because the world is very big, and you should take an opportunity or any kind of opportunity to get experiences on that. Okay, so moving on. So after serving in the military, and I end up applying to graduate school, and I mentioned before, by the end of my college years, I decided not to be a civil engineer. I wanted to do applied math, right? I wanted to be an applied mathematician. So when I applied to graduate school, I am looking for the program which is so-called applied mathematics program. Again, I want to remind you that that's in 1969 or 68 to 69. That's when I applied to graduate school. We didn't have internet, right? We didn't have a computer. We didn't have the internet. We didn't have a cell phone. Right? So can you imagine that kind of life, right? And I was in the army. Half the time I'm in a tank, right? But I have to, under that kind of environments, I have to apply to graduate school. I somehow made it happen. And we have to go to the library, which is supported by the American Embassy. We did have an American Embassy in Taipei at the time. And we had to go to the library, flip through the catalogs and to find out the different university and different opportunities, so on and so forth. But applied math is a very small program anywhere in the world. So it's very difficult to actually fund a few of them. But so I end up adding some other programs, some other universities, which has some fluid mechanics programs. And I'm thinking that they might be kind of related. But anyway, make a long story short, I got into MIT and the fluid mechanics hydrodynamic program and at the time. So I don't know why they picked me, because you remember I almost failed the calculus course in the freshman, right? But my only justification is that my grades probably had a great jump in the sophomore year and probably maintained pretty high level, higher mark for the rest of my college life. And also perhaps because we just have a pretty whole bunch of crazy classmates who all went out to take different courses from other departments. We all get killed to a certain extent, right? We don't get A pluses in the physics department when you take advanced physics, competing with a physics major, or you don't get the A plus in applied math, with competing with math students. So anyway, our grade wasn't all that great, but somehow MIT likes it, that kind of pictures. So they took me in, and so here I go. I went to MIT, and I stayed there for about 5 years. And I was in the program called Hydrodynamics and the Water Resources program. Right? And the first year I was there as assistant professor, I get a scholarship, I get assistantship. And I was assigned to a professor to do the laboratory experiments. Remember, I want to do math, but I was assigned to do laboratory experiments. And in fact, it's a very interesting experiment. Some of the hydrologists, I saw some people here, that is trying to use the so-called hot wire anemometer, the hot wire to measure the velocity in the porous media. That porous media flow is driven by the airflow. Okay, so you can imagine that this is equivalent to say you have airflow blowing over canopy, and the canopy is some kind of porous media flow, and you use a hot wire and to measure the airflow velocity inside and outside the porous media. That is 1969. Okay, it's very advanced technologies to do such kind of measurements, right? And it's a brand new technology actually. And I didn't know anything about experiments. Taida didn't teach me that. That's one thing I think Taida should teach experimental work, okay? Taida didn't teach me that. And I didn't take any turbulence courses at all, right? And but I was forced into it. Say, you're assigned to this project to help the PhD student, Jim Ruff, to finish his PhD work. And what we do is that we do these experiments in the detail. So I was pushing to put in the situation that you have no choice, right? Remember, we were not rich. My family wasn't a rich family, so I really need that assistantship to survive, right? And so this is so-called 中国人, well, we say the 背水一战, right? There's no place to go, and you just because you need to survive, then you study it, right? You accept the challenge, you put the best foot forward, and learn something from it. Right? So after 1 year, I learned the turbulence. I learned how to do the laboratory experiments, and also did an analysis for the data. So MIT is a great place. That's a typical MIT, right? And it's like put it in the spot and just try to swim yourself, and you learn it, all right? And the professor probably will help you a little bit here and there, give you a hint, but mostly you really have to do it. You have to learn the stuff yourself. Don't wait until I take those courses, then I can do this. Too late, all right? And you have to be self-motivated. You have to be, to do all this work yourself. But it's a twist of luck or whatnot. But by the end of the first year semester, the beginning of the summertime, and somehow Professor May, some of you know him. Somehow he approached me and to say, well, I have this interesting project and using perturbation method to do wave theories. You remember, this is just 1 year away from when I applied at MIT. I thought I want to do a math. Right? This is really an opportunity that I say I cannot pass on. Not that I don't like the turbulence or the experiments, but this is just something that I always wanted. So I accept his offer, I switch over, and the rest of the story is a history. Right? So for the second year on, I actually study under Professor May, May Qiangzong. He also is 台大校友. Okay, I forgot which year, maybe 10 or 11 or 12 years older than me. And in fact, recently I discovered he wrote a bachelor degree thesis in civil engineering and in English. In English, and it's in the library. I have a copy of it, and it's amazing. It's a quite amazing thing. And anyway, Professor May really taught me everything about how to do research, how to do perturbation, I guess, and how to do the nonlinear wave analysis. And what's more important is not the detailed knowledge, is the philosophy, the attitude, how he approaches research, all right? How insists that that you have to be able to follow through all the detail, and at the end, when you get to the result, you have to be able to explain everything from the physical point of view, all right? So mathematics basically is a tool, right? Help you to organize your thought, try to interpret the physical process. That's all. Right? I guess I'm not a true mathematician because I really use mathematics as a tool to really understand the physical process. And Professor May has amazing physical intuition on a lot of a physical problem, and that's also important, right? Because in the perturbation methods, the basic trick is how do you figure out the different kind of scales in time and space for different flow field or different kind of process, and enable you to determine what is small parameter in the perturbation methods. Right? So somehow he has that intuition, and that's hard to copy. But if you talk to him long enough, and I think you something rub off on that. Okay. By the way, this is my master thesis. So basically, it's looking the damping of a surface wave, gravity wave, in the bounded liquid. That means that you're looking at the boundary layer flow near the solid surface and also near the free surface. And what is the contribution? Well, contribution really is that for the first time, we were able to use the perturbation theory to explain how the energy is transferred from the core region to the boundary layers, the solid boundary layer and the free surface boundary layer, especially to explain the energy transfer from the solid boundary to the free surface boundary layer through the so-called meniscus regions. That's the interface region, interfacial region between surface and the boundary, free surface and boundary. So anyway, so that was my first paper actually in Journal of Fluid Mechanics, and I was quite proud of it. Right? Now, this is a little bit kind of a bragging about how good is MIT. I don't know how to describe it. If you believe getting elected to NAE is some measure of the achievements or accomplishment of research. Right? So this is just one small window from 69 to 74. At the time, Professor Holloman, Eagleson, May, and Itobe, they were all professors at the time in that group, in the water resources and hydrodynamics. They were not elected they were young. Professor May is only associate professor. Ignacio Itobe was only assistant professor. I guess those other two, Peter Eagleson and Donald Holloman, was more senior. But 10 years later, they all get elected to NAE. Right? That's the faculty. But my classmates, right, at the time, over that small window, about something like 5 years. Right? We didn't have a very large group of people. But Eric Wood from Princeton, Jerry Cohen from the Carnegie Mellon, Raphael Brass, of course, MIT, then went to Georgia Tech, and Dick Hughes, MIT, and myself, Cornell. 20 years later, we all get into the NAE. Right? So MIT somehow prepare you, provide you the tools to do research in the sound way, and also their faculty staff, the quality is definitely there. So all I'm saying is that if you have a chance, right, doesn't have to be MIT. When you are looking for people to work with, when you're looking for the organization to work with, quality, join the best quality group you can, right? And the group is going to elevate you. You are going to help the group, of course, in a mutual way. So aiming for higher, and that is going to be beneficial for your career. That's for sure. Okay, after I graduated from MIT, so I went to Cornell, right? And actually I drove from Boston after I finished the thesis to Cornell, which is in Ithaca, New York. And that's about 10 hours drive. And this is a beautiful town. And I stayed there for almost more than 40 years. I never left. And what I can say about Cornell is, again, it's an amazing place. It's not like at all like MIT. And MIT is very busy, everything is too late when you do it. But Cornell is more relaxed, laid back. And in some way, I almost feel that Cornell is a lot more scholarly. Right? And perhaps that also reflects on some of the type of research we do. And we're not in a hurry to do it, but we get it done. We get it done in the right way. Right? And again, if you use NAE membership as a yardsticks, and in our little group in hydraulics, water resources, we do have quite a few NAE members. Eventually, over these years I've been there, and then there's other people from the structure engineering, structure and geotech engineering. Right? So again, now I guess at a point when I decided my career, when I graduated from MIT, how did I make that decision, right? Thinking back, I say, did I really think that hard? Do I really think that I know what I want? Should I go back to Taiwan? Should I go to the other country, or should I just stay at MIT? In fact, I had opportunities to stay at MIT as a research associate, I guess. This opportunity also just came up out of blue, actually. The advertisement of this job coming very, very late, and when I graduate, just about to graduate, and so I was almost the last one to apply for this job. And when I interview it, they literally just offered me the job on the spot, right? But it's not that because I'm so good. I guess just timing is right, and the kind of a person they want, I happen to be the one, right? Now, why do I take that job, right? I could maybe stay at MIT and honestly, I don't know, right? I think Cornell job at the time is a lot more challenge, because if I stay at MIT, I will be working with Professor May, still under his protection, basically. And this is like to be independent, get into the new environments. Just like I moved from Taiwan to United States, did I know what I got into? No, not at all, okay? And I never been in an airplane before I took that charter flight to United States. I never spoke English with anybody except in the class, all right, English class. But I threw myself into this new environments and just say, well, I want to learn more, I want to study, so this is a chance I'm going to do it. And whatever happened, I'm going to accept the challenge. Here's a risk, I'm going to trying to overcome it. I think this is the same thing here. I took on the Cornell job, not knowing exactly what is the best optimized solution, but I take a chance, right? And then try and then put the best foot forward and to do it. So I guess if there is a message here is that I know nowadays when I talk to some of my younger PhD students, I think these generation students tend to be a lot more practical. They overanalyze their life, right? This is what I want to do 5 years from now. I'm going to get married, I want kids, and I need to have this, have that. And they think long term, right? And I have to write 5 papers. They haven't even started research. They're telling me that I have to, they want to write 5 papers because they want to get promoted or get accepted to the university. They want 7 papers. So anyway, so I really think that you shouldn't do that. I mean, there's no optimal solution because you don't know. There's a lot of uncertainties involved. But instead, you should ask yourself whether this is something you really like to do, right? I think part of this, coming to Cornell, I like the environments, I like the research area that they say I can get into, and then I jump in it, right? So ask yourself whether that is what you really want to do, what you like to do. Don't overanalyze everything, otherwise you probably will hesitate to do anything, right? Okay, so then of course, as President Chen says that 2015, there was an opportunity that was recruited by Singapore, University of Singapore, to become their vice president for research and technology, and for very selfish reasons, I went. Selfish reason is that it's closer to Taiwan, right? And they pay better. But no, that's a joke. But so there's other good reasons I decided to go there to say, well, okay, I have done some administrative work before as the department head, department chair, and also I was vice dean for the engineering, associate dean for the engineering before. I said maybe I can try it again in an even higher level. So also Singapore is such an intriguing place, right? To try it out. Again, it's not my adventurous spirits to say, okay, why not try it, all right? And giving me an opportunity actually getting closer to Asia, sort of like coming back home halfway at least. So I stayed there until 2023. And of course, we went through this COVID period, and everybody had that experiences. All right. So, a little bit of my research now. What time is it? Okay, so I can wrap this up pretty quick and let you guys ask me questions, right? So that almost wrap up with my sort of little story here and there about my journeys going from the high school student all the way now to the retired person, all right? And so quickly about some of my research work, very sketchy. There's some equation, you can ignore it, right? Now, this is an interesting point here. This is the first big topics I get involved when I moved to Cornell. Right? Remember, I was doing experiments the first year at MIT. I spent the next 4 years doing theoretical work with Professor May in water wave as a related problem. Then I went to the Cornell. And a colleague of mine, that's another thing. The good thing about having a good environment is Cornell is a very collaborative kind of environment. MIT probably is the last, right? They're pretty cutthroat. Right? MIT, Cornell is a little more collaborative. So this is senior professor Jim Liggett. He actually come to me, I was a junior faculty member, say, wow, I have this idea to use the so-called boundary integral equation methods, right? And why don't we work together on the free surface flow problem? Because he thinks that I know more about free surface flow, right? Wave, right? So actually we bang our head together and we work on this for several years. And we actually developed systematically probably the first attempt of formulating this free surface flow. This book is based on for the groundwater flow and type of problem, and using the so-called integral equation method to do the computation. So it's a mathematical or numerical methods type of book. And in fact, my first PhD student, Jared Lennon, wrote a thesis on this. In fact, he's the one become a vice provost at the Lehigh University and retired by now. Right. So he graduated in 1980. That's 40 years ago, right? All right. Okay, so that's the thing, and that's the first topics. I think we have some contributions to the academic world, and other things I have done, like Professor Chen mentioned that I was quite involved for many years, and still right now on the so-called tsunami research. There's a very long story on this, and in 1960-64, there were a couple of tsunamis happened, and actually inundated Hawaii and Alaska, caused some damages. So at the time, the federal government or U.S. government putting some funding, trying to say, okay, let's try to understand what is tsunami, especially what is a tsunami generated by the earthquake, related earthquake, and how do we actually predict it if we can, and how do we establish a warning system on that. But from 1960 to 64 or 68 all the way to the 70s, 80s, there was no really big tsunami happening. All right, so the tsunami, the research funding is going down and down. This is the typical, right? The typical kind of attitude when you deal with a natural hazard. When there's a one big hazard happen, then all of a sudden everybody said this is the most important things, and then after a while everybody forget about it. And research funding situation is the same thing. But fortunately, at a time when I graduated, I was 74 and 75, at the time there was a program manager, Dr. Cliff Astow at National Science Foundation. He really has this far side. He says, I'm going to support a small program in the United States to do tsunami research. So we want to maintain that level, certain level of research competence, so that in case something happens, we know how to deal with it, right? And in fact, hopefully we can really continue to develop what we need to do, like how to monitor the tsunami or how to do the forecasting. So I was lucky being in the right place at the right time. And with his support, I worked with quite a few peoples, and together for many, many years. These are some key figures. This is Cliff Astle, okay? And this Costas Sinelakis from USC. This is George Carrier. Anybody who studied applied math probably heard about his name, right? Complex variable person, and is everything else, actually, right? And he get a presidential medal or something in the United States and for his work. And then Fred Reichland and Caltech. Carrier was at Harvard at the time, and Harry Ye at the Washington State at the time. So we sort of a group becomes a small group of team, the core team, and to work on the tsunami research in the United States. We practically get continual funding from NSF. I don't know how ASTO managed it, okay? But somehow or other, we have pretty much continuous support from him, this group. The philosophy or the approach at the time was that we recognized immediately the tsunami is an international hazard. There's no boundary, so require international collaboration. So we have to work with the Japanese and other country like Russia and other countries, right, to work on this. In terms of sharing data, sharing the information, sharing the development of the hardware, right, for the instrumentations to measure the tsunami. And then also to establish any kind of forecasting models or technique. And we do this kind of research require integrated approach in terms including theoretical, numerical, and experimental work. All right. So all 4 or 5 of us in that group, actually each one of it has different expertise. For example, Harry Ye was very good at both experimental work and some analytical work, right? And George Carrier, of course, is a theoretician, applied mathematician, basically. Fred Reichling is basically the experimental person. Costas eventually developing the field person, doing a lot of field observation type of work. So we try to work. We invite other people get involved and expanding the communities and to get more people involved. Right? At the end of the day, we want to develop some kind of tsunami monitoring system and also the early warning system. Right? That's what actually in place right now in the Pacific Ring. In other countries, in Japan, in the similar kind of systems. Okay, so one thing we really do is to organize workshop, small workshop, not a big conferences, many thousand people. We have maybe 50 people, so that all the magnitudes invited the experts to participate in it. And if you are in the coastal engineering field, these are the people actually are pretty well-known people even at the time, including some Russians. And Eddie Bernard is in charge of NOAA, in the NOAA lab, marine lab in Seattle. There's a laboratory. Eventually, they developed the instrumentation to measure the tsunami in the oceans, right? And we actually started to develop some numerical methods, models to help in terms of forecasting. All right, so this is we organized this first long wave workshop, and so actually get a whole international group together and to look at the problem, thinking about this problem collectively. All right, so that is a really important aspect of this research. Okay, another thing is that for some reasons, again, we didn't plan for this, but after we started to think about this, organize these workshops, so on and so forth, getting our act together, in the 1990s, there were quite a few large earthquakes and generated tsunamis. All right, and so one thing we decided to do is that we have to get the data. We have to get the data. So we have to do some field survey after the tsunami, after the events. And for example, in 1992, Flores Island tsunami, that's in Indonesia, Right? That's the first internationally organized survey team, including the people from Japan and some Indonesian, of course, and the United States. And together, we actually went to the Flores Islands and did a detailed tsunami surveys, measuring the runoff height, the inundation areas after the tsunami along the coast of the Flores Islands. These are the pictures, and we published papers for this, the results. And one of the particular interesting thing is that during the tsunami surveys, and we observe a very interesting phenomenon, which is that in the one of the small islands, so-called Bobby Island, I think this is the Bobby Island. No, maybe not. In one of the small offshore island, few kilometers in diameters, and the tsunami is attacking from the offshore in this directions, but there are two villages behind in the lee side of these islands, and actually get totally destroyed by the tsunami. Right? You would think that if you think about waves coming from this direction, and the lee side will be protected as in the shelter regions, right? So at the time, we were just very puzzled. Can we explain this in a more detailed way to understand this process? And so we brought this problem from the field, collecting the data, information, bathymetry, and back into the laboratory. And then we did experiments, all right? So this is the model of the islands, and we put in the wave basin here, and then create the wave coming in from this direction. And indeed, you see the run-up at the lee side actually is much higher. And actually, after you saw that, you say, that's kind of obvious, because the wavelength of a wave is so long, and these two waves is simply wrapping around the islands and collides into each other in the lee side. And that means that will increase the run-up height in the lee side. Right? If your wave is very short, like a wind wave, right, the wavelength is only 100 meters or so. This tsunami is about kilometers long, okay, or a few kilometers long. So it's very long, longer than the island itself sometimes. And so the phenomena is quite different. And so we also developed a model, take this opportunities, actually construct a model, what we call the COMCA models, and to simulate the generation of a tsunami and propagation of tsunami, and also the refraction, diffraction of tsunamis. Then this model actually becomes pretty popular and useful for other type of tsunami research. Right. So this is just a simple example, is that the combination integrating the field work, field data, and the laboratory work, and eventually with the numerical work. And not only validating the numerical models, and which enable one to use these models to further simulation or further forecasting purpose. Right? Okay, so this is COMCA type of model results. Basically, I'm not going to show you the equation. It's a solving shallow water wave equation. All right, and if you can prescribe the so-called prescribe the source region of the earthquake. I can make this happen. Okay, never mind. So then you can do the simulation to calculate how the wave is generated and propagates. In this right-hand side here, basically is fictitious case and didn't really happen. The one on the left is something that is actually is 2000. Is the Indian Ocean tsunami. I cannot see my pointer. Where is it? Here we go. Okay, so this is the tsunami simulating the Indian Ocean tsunamis. They starting from the Sumatra trench and generated wave propagating over the over the Bay of Bengal and going attacking the Sri Lanka and then India and all the way across. All right. And the right-hand side is a fictitious case that if we have an earthquake in the Manila Trench, northern part of Manila Trench, and what kind of tsunami could be generated, whether that will affect Taiwan or not. Answer is yes, if the tsunami earthquake is strong enough, maybe magnitude of 8 for sample, and actually will affect the southern part of Taiwan. In fact, Tainan or Kaohsiung will be affected, right? And so these kind of models has been used for various kind of research purpose, and also in developing the more forecasting issues, forecasting problems. All right. I'm going to skip over this. Now we, as President Chen said, that we actually published quite a few review kind of books and trying to summarizing or updating the research new informations in the wave theories and also tsunamis. All right, quickly, just very, very quickly, some of the other, I say groundbreaking, probably a little bit too strong. Front running probably is more appropriate. You know, some of the research we did at the time was considered as a brand new, as a leading kind of edge type of research. And of course, this is all done a long time ago now. Now it becomes kind of where people say that's pretty routine now. Right? So this is the first work in 1998 by my student Peng Ziling. He is a professor in Sichuan University now. Now we actually developed this model, is solving two-dimensional free surface flow problem, including water wave, breaking wave, and with the consideration of turbulence. All right, turbulence generated by breaking in this case, and this is at the time was the first one that actually demonstrating at least that that's doable, and in fact we'll compare with some laboratory experiments getting reasonable agreement, and that opened up the doors. And now every day you look at journals, a lot of this similar type of work. All right, and then again in similar type of time, another student of mine, Quan Chen, who also is a Taida graduate. Okay. And he has a very interesting background. He actually graduated, he has a technical degree, right? Gongzhuan or something in electronics. Then he came to NTU, get a bachelor degree, I think in ag engineering at the time, I'm not sure. But anyway, he is very good at instrumentation. He likes electronics, and I get him in. At the time I have this, I read something in the literature say this PIV, particle imaging velocimeter, is a new thing in non-intrusive method to measure flow field velocity, right? Usually we use a probe to measure the velocity in the flow field. That's intrusive. You will disturb the flow field. Now particle imaging velocimeter is using imaging technique, take a picture, and you see the flow field with some particles, they track the particle. And then you figure out, use statistical method and figure out what is the velocity inside the flow field. I say, well, we in the wave field, we have all these problems, measuring the flow field, say near the, in the breaking wave condition or near breaking wave conditions, all right? Because any kind of disturbance in the water is going to change the flow field. Right? So why not try the PIV methods? That's in way before 1998. I said, well, why don't we I just write a proposal, and staff says, let's do it. Let's try to do it. Nobody has done it before, doesn't matter. That has been proven in other type of flow field. Maybe we can have a luck, and with some modification, and we can do this. And so Quan An was very brave, and we worked together and put all these package together. Practically, we did it by ourselves, and then by the laser, by the cameras, and so on and so forth. And we actually did it for the first time. Wasn't perfect, and there's a lot of issues like the shadowing techniques, and but nevertheless, it's a brown. This again open the door for lots and lots of future research in these areas, right? All right, so this is another part of my life career. Basically, as a coastal engineers, now we look at a lot of problems in the so-called shallow water wave in the near shore, but we always like to bring the wave from deep water to the shallow water, right? So most of the wave theory or models in the shallow water doesn't work for the deep water wave, right? So the dream is always that can we have a unified mathematical model or numerical model, and can bring the wave all the way from the deep water to the very shallow water, and in between that you can look at a kind of different kind of wave process. So this kind of research actually occupies a lot of people times in those years in the mid-90s, even to now, people still working on this. So I have quite a few students who have written PhD thesis on it, and Xiao Sijun is one of them in 2000. And Pat Lynette is another student. Wu Zhuoren is also involved in some of these activities. Even more recently, after I went to NUS in Singapore, and one of my Singapore students, PhD students, actually developed a type of model I think is much better than everything else we have done before. All right, as far as the capability of bringing wave from really deep water to really shallow water, without breaking, of course, right now. And but this is life, right? I mean, sometimes you have to do things incrementally, and you learn, and then you make improvements, right? Then eventually, hopefully, you will achieve your goal. So there are two papers, especially in this kind of models has been working on, including the currents in the models, right? So the other components, other kind of aspect of my research has something to do with sediment transport. In coastal engineering, there are two things. One is a wave, one current, then the other thing is sediment transport, how the beach deform, how the coastline changes. That all has something to do with sediment transport. But in civil engineering, usually we use a lot of empirical formulas to calculate sediment transport. And basically you separate the flow hydrodynamics from the sediment transport mode, right? And so we're trying to look at things from a little bit different perspective, to look at more fundamental process. So how the sediment particle, for example, if they are granular materials, how the particle motions generate turbulence, and how the turbulence of the flow field interacting with the sediment motion, particle motions. So a lot more smaller scale process involved in there. So Tang Xu, again, is NTU, is Taida's校友. Okay, I think he graduated civil engineering, I think. No, he graduated from ocean engineering. Huh? 造船, okay. So it's 前身, right? It's 造船系, right? But anyway, so he is at Delaware. By the way, Guang'an is in Texas A&M right now, professor at Texas A&M. And so Xiao Sijun is in Chengkong University. And then Tang Xu, Xu Tianjian, he is at the University of Delaware, which has one of the very best coastal engineering laboratory or program. And he probably is now the best, one of the best people who actually study, able to understand the sediment dynamics, and in terms of these two phases interactions type of problem, right? And I simply point out the directions, and he did a really nice job as a first piece of work. Then later on, there are other two PhD students continue on that and improving on this. And I think there's a very bright futures for this area still, a lot of work to do. Now, then we try to extend the so-called 2D CFD type of model to 3D with the turbulent closure models. And the thesis written by Wu Zuoren is the results of this piece of work. We also did some experiments and to validate the model, right? And I wrote down here at the time, it's really way ahead of everybody. Not many people can do this kind of 3D analysis anyway. But now I guess things has been improved and people have already make some advances in the field. But at the time, this is really pretty gone through. Now I mentioned that in the Indian Ocean tsunami 2004 actually, and that is the big tsunami in Indian Ocean and killed more than 200,000 people in many countries. And I was actually I led a team of researchers and engineers and went to the Sri Lankas to do the surveys along the entire country on the East Coast and the West Coast. And so it is a real heartbroken experiences to go to the country under the circumstances, especially that still during the Civil War. All right, you can see the devastating situations by man-made disaster and the natural disasters. And so it is what it is. And we got some scientific data out and validated some of our models, numerical models. That's a very important set of data because between the source region, the Sumatra zone to Sri Lanka, there's nothing in between. So it's a wide open, so-called open ocean space. We can validate the tsunami models very without any kind of approximations, right? More realistic. And so there are other surveys, and 2011, that's the Japanese Tohoku tsunamis, earthquake and tsunami, and a week or so later we went there. I was dead tired. This picture actually show you the face. This guy is sleeping. And we went from the United States, landed in Tokyo and drove all the way up to the Tohoku. And it was really something else. So this is Harry Ye, this is Professor Shuto in Tohoku universities. Okay. All right, so the story, I didn't stop there when I went to the Sri Lanka, went to the NUS, and there was another earthquake, tsunamis happening in the neighborhood in the Indonesia, Palu tsunami. And this tsunami actually was not directly generated by the earthquake per se, it's generated by the so-called landslide combinations. Right? And that opens up another questions about how do you actually model the landslide generated tsunamis, and that's a lot more difficult problem, all right, than the earthquake. Earthquake is tough enough, but landslides. Okay, I know my time's really up, and I should totally wrap up. My last student is only female students. I'm sorry, female PhD student, so I have to mention her name. All right, Yufei, Wang Yufei in NUS, and so what she did, and with other people at Kui Feng. Look at some very classical fundamental wave mechanics problem. The Stokes wave, everybody probably heard about Stokes wave, and also heard about solitary wave. We'll look at a fully nonlinear solitary wave, fully nonlinear Stokes wave. Surprise, surprise, we find a lot of problem with a theory which has been used for 50 years. Right? I'm not going to tell you the thing because I don't have time, but just believe me that look at these papers, you'll find out that Stokes wave, fifth order Stokes wave in the water wave, right? Theory, people have used one theory developed by Fenton since 1985, but we show that he used some artificial assumptions which is not only not necessary, but also that if he used that, he couldn't satisfy the actual free surface boundary condition, so on and so forth. And so we correct that. So this is kind of interesting to me, and after so many years, but this is such a fundamental problem that we feel pretty good about that. Now, UFA did a solitary wave type of a problem. All right, so these are the picture headshots of my Cornell students. Most of them are in the university, as I mentioned. Most of them stay in one job in the university. You can say that they have no place else to go, or you can say they really love their job, right? And I think they do. I think the latter is true. They are scattered all over the world. And then these are the few snapshots of students and the PhD, the postdocs at the NUS. And most of them are postdocs. I only have about 4 PhD students in this group. And okay, so that's it. So these are the distribution of my PhD students, former students, and I guess I want to summarize what I said, but I don't think I have to say it again. So the bottom line here is that, hey, nothing is really smooth sailing, right? I mean, you can fail easily sometimes. It's a question about resilience, right? Whether you can bounce back, and then you sure have the courage to bounce back. You learn that from your failure. Your mother tell you that all the time, but it's true, right? And so stick to the hard work. I mean, do some hard work in certain area you find it hard to do, and maybe you'll find out you actually like it, right? And if you do put in the hard work, you never enjoy it, the fruit. So again, you know that, right? Then I say university. I said that before. The university journey is very important. The 4 years. Don't let it go on. Don't let play the game all the time. And use this opportunity. Make some friends. Not too many friends, and few friends, and also find out who you are. Seriously, I'm serious. Find out who you are, right? And this is the place that allow you to make mistakes, right? This is the place actually very flexible, and you can come back if you make mistake, change your direction. That's easy, right? So, and the last thing is that you should choose your careers that you really enjoy, right? And the monetary things will probably come if you're successfully doing something, and maybe you can just reduce your desire to have a material life. That's not really that important. You really want to enjoy your life. Working is a significant part of your life, right? And somehow develop the mental capability of being curious, looking at things. Don't put your head down all the time. Look around. Observe, be curious, ask questions, challenge the professors. I always tell my students that don't believe everything I said, just like I tell you now, don't believe what I said. Ask the question and find out yourself is true or not, right? And nowadays you have so much information. That's really, really, really important, right? And you have to be able to find out what is true, what is not true. And be brave. Set up your comfort zone, right? Step out of your comfort zone and try something different and take a risk, right? And no big deal. I mean, if you fail a little bit, right? And then be kind to yourself. I mean, if you fail, forgive yourself a little bit, right? And give yourself another chance. And then, most importantly, be nice to the people around you. And I get where I am. It's not all by myself. I didn't do it all by myself. You can see all the professors, Professor Ye Caoxiong, Professor May, they helped me all the way along. Even after I graduated, right? They helped me to help me in my careers. And Professor Liggins and others at Cornell, and pull me up and help me to put in the right place. I have all the collaborators in the world. I have all my students. I think that's the best part of my life, right? With all these students that I interact with them. I work with them when they are they are at the peak of their career, meaning PhD student period, at the best time, the high power time, and I had the opportunity to work with them. And in fact, I keep in good contact with them and keep me refreshed, and that is really the perfect situation for me. So I spent way too much time. Thank you very much. If you have any questions, I'll be happy to answer.
Thank you.